Yeah, hello everyone, and welcome to this British Society for Geomorphology webinar. If you're not a member, please do consider joining. It's an excellent little community of geomorphologists from a range of different, fields within geomorphology: fluvial geomorphologists, coastal, glacial, lots of interest there. Yeah, please have a look on the website to see what membership can offer. One of the things is that you will be put on the mailing list for these seminars, so you will never miss one in the upcoming future. There's lots of really exciting talks planned for the rest of the year. So yeah, I really do recommend being on the mailing list. It's a pleasure today to welcome Ben Meredith. Ben's a senior advisor in risk assessment and research at the Environment Agency. He's got a background as a geographer, and he built his career with the Environment Agency in their flood and coastal erosion risk teams over the last 17 years. For the last few years, he's been the technical lead for a comprehensive update to the National Coastal Erosion Risk Mapping for England. And he'll be speaking to us today about the recent updates to the NSERM project, the data from which was released earlier this year. Well, thank you for speaking with us today, Ben, and now I'll hand over to you.
Thank you very much, Nish. Well, hello everybody. Thanks for joining, and thanks very much for giving me some time today to introduce the National Coastal Erosion Risk Mapping for you. So today I'll take us through quite a detailed insight into the National Coastal Erosion Risk Mapping. It's also referred to as NSERM throughout this presentation, so that's the acronym that you will see quite a lot. I will start off by updating you on the new and updated flood risk and erosion products that have been launched this year by the Environment Agency, before focusing in on the coastal erosion risk data. I'll provide you with a brief introduction to the NSERM product, followed by a more detailed look into the methods and the data used to produce it, and then tell you where you can find the information. We will have time for a discussion at the end of the presentation, where I'll try my very best to answer any questions that you might have, but I'm also keen to gain your comments and your expertise and thoughts for future improvements and developments as well. So the Environment Agency and our partners have been on a bit of a risk data journey over the last few years, with a major revamp of our national flood and coastal erosion risk products. This has not been a case of just getting new data to feed our risk models, but a complete new modelling system and methodology for our National Flood Risk Assessment, NAFRA, which now produces all of our national flood risk information products, including the risk of flooding from rivers and sea and our flood map for planning service, and of course a substantial revamp of the methods and data for the coastal erosion risk mapping, which will form the discussion today. We started publication of the new data in December of last year with the National Assessment of Flood and Erosion Risk in England report, and that set out the improvements that we've made and the changes to the national picture of risk for England. On the 28th of January, we then published the new risk of flooding from rivers and sea on Check Your Long-Term Flood Risk Service and the National Coastal Erosion Risk Mapping data on our Shoreline Management Plan Explorer website. And this was followed by the publication of the flood map for planning flood zone data on the 25th of March. Obviously, these data sets are critical for communicating risk to a really wide range of stakeholders and audiences, and a key part of the Environment Agency's strategic overview role for all sources of flooding and coastal erosion risk, and also in developing and applying the National Flood and Coastal Erosion Risk Management Strategy. So let's now spend the rest of the session and draw our focus into the coastal erosion risk mapping. I do want to take a quick look at the basics of what NSERM is. So it was developed originally back between 2006 and 2012 in order to provide planners and the public with an easy to use tool to show erosion risk for England and Wales. It provides predictions of erosion distances around the coast, set time periods that are defined in the shoreline management plans. It uses a whole range of data sources, which include geology, observed historic erosion, coastal defences, the shoreline management plans themselves, and local authority information as well. Previously, the erosion estimates were shown as a line along the coast on a GIS mapping system, with erosion predictions in a table like you can see on the image here. It provides important risk information to identify locations and numbers of properties at risk, inform local planning decisions, including coastal change management areas, adaptive planning decisions, and investment along our coast. So in 2020, the Environment Agency committed to updating the NSERM as a part of the National Flood and Coastal Erosion Risk Management Strategy for England. The project was funded and managed by the Environment Agency, but the NSERM product is dependent upon local authorities on the coast providing local information and also verifying the data as well. Local authorities, of course, have the remit for erosion risk management and so often hold that specialist knowledge for their local coastlines. For that reason, throughout the project, we've ensured strong representation of local authorities on our project board and our technical advisory group. And we continue to work really closely with the coastal groups around England and the local government association, Coastal SIG, as well. So at the start of the project, we set out with some broad aims to make more reliable technical product using new data and research and development to improve the methods where we could. We wanted to make the data more accessible and easy to understand using the new shoreline management plans and the Explorer website and having better visualization. We wanted to improve the maintenance of the data set as well, bringing that in line with any updates with the shoreline management plans. I've mentioned this already. Throughout the project, we work collaboratively with partners on our project governance groups and directly with local authorities to ensure that the right data was being used to create sensible projections of erosion risk. And we also wanted to update our analysis of the receptors at risk from erosion. So we saw on a previous slide what NSERM looks like from the ArcGIS online page, which is the image on the left here, supplied as that single line with an accompanying table. And right at the core of the ambition for our project was to move from the image on the left to a much more intuitive and easy to use product, which shows erosion data visually as areas of potential risk, whilst also providing supportive data and text to aid better understanding, moving much more towards the early days prototype for the SMP Explorer that you see here on the right-hand side. And it was really important for us to have the information on the Shoreline Management Plan Explorer website, because that allows users to access not only the erosion risk, but also the detail behind how we plan to manage the coast in the future. I wanted to briefly outline how we conducted the project. It was a large national project. We employed consultant Jacobs as our primary consultant, who brought 2 subcontractors with them, Royal Haskoning DHB and the Channel Coastal Observatory. So clearly a knowledgeable and experienced team focused on coastal management and engineering projects, and of course the national network of regional coastal monitoring programs which collect and quality assess and supply the coastal monitoring data. We tackled the project in 2 phases of work. Firstly, exploring the new data that was available, the research and development that we could bring through, and any methodology improvements that we're also implementing at a national scale. And then during phase 2, we brought those improvements into the process and put them into action. We had extensive data collection activities, bringing in national data from the Coastal Monitoring Programme, Environment Agency data sets, and of course, local authority information. As a project, we put a large set of time and resource into verifying all of the input and output data, and a huge commitment was given to us by our stakeholders to assist in this work. We also had great assistance and support from the Coastal Group Network, and that ensured that the project was well supported and that key stakeholders were kept up to date with what was going on. So it really has been a very collaborative project, making use of all the expertise from various organisations and groups around the coast. So before, excuse me, before I go into the improvements that we've made, it is worth setting out some of the key principles behind the erosion risk mapping. Whilst we've done a great deal of work to obtain local information and reviewed it at a local scale, NSERM still is a national scale product. So for large areas of the coastline, it will be the best and only erosion projection available. But in many places, there are local studies which will be more in depth and use different, more detailed methods. And we have brought data in from those where it's been possible to do. The mapping does not show the position of the future coastline. This is a very important point. It provides an indicative zone of erosion risk, identifying areas which may experience erosion over the timescales shown under the model scenarios. We don't map the residual risk of erosion behind defence locations either, where it is hold the line and defended. It presumes that no erosion occurs behind these defences, but in reality, of course, there are defended locations which still experience erosion of cliffs and slopes behind them through other processes other than just from the sea. NSERM shows erosion risk to areas of generally higher ground. So where part of the coast is predominantly flood risk, we don't show any erosion projection for those locations. The core management scenarios that we look at are with shoreline management plans delivered and no future intervention. And I'll go on to these in the following slides. The NSERM dataset has always been and continues to be available as open data for people to access freely. So what erosion scenarios do we use? So NSERM uses the shoreline management plans, approaches and timeframes alongside UK Climate Projections 2018 sea level rise information. And it uses both those to provide a range of erosion risk scenarios. The SMPs, shoreline management plan approaches, are used by NSERM to determine how a stretch of coast may be managed now and into the future. And NSERM uses the information in the with SMP delivered scenario to define if a location is essentially defended or not. NSERM also produces a no future intervention management scenario where investment in coastal defences ceases. Defences then deteriorate and fail over time and erosion takes place. So this is a hypothetical worst case scenario, and it's there so that we can see the benefits of coastal erosion management and investment. In terms of climates, NSERM uses sea level rise data from the UK CP18 to increase erosion rates and to reduce the lifespan of coastal defences. We use two sea level rise projections from UK CP18 representative concentration pathway 8.5. These are the 70th and the 95th percentiles, known as higher central and upper end in the Environment Agency's flood risk assessment and flood risk modelling guidance for sea level rise. NSERM therefore has three climate scenarios: a present day climate where erosion continues at the same rate as recorded so far, and then that higher and upper sea level rise scenarios. And it shows the likely areas at risk of coastal erosion for 2 points in the future, the years 2055 and 2105. And those years are taken directly from the shoreline management plan epochs. So during the NSERM project, we made improvements across all of the areas that you can see on the screen here, as well as bringing in as much current data as possible. And I'll go through each of these during the remaining slides in this session. So moving into the methodology and the technical methods that we used. So this schematic here shows the modelling process that we used for NSERM, taking observed coastal data on erosion and using that to create underlying recession timelines. We also looked at the defences and their potential for failure and included climate change impact on those. For defences, we also consider the effect of erosion catch-up once a defence fails. We use those underlying recession and defence failure timelines to create an overall timeline of erosion distance through time, which we can then adjust for the shoreline management plan approaches at relevant locations. We then produce our mapped outputs, which show erosion risk zones, taking account of the zone between the cliff top and the mean high water spring line, and we produce confidence ratings for the data. And I'll go through each one of the stages on this slide in the coming minutes. So the feature line is the first critical step of our process. This was previously called the baseline and then zone 1, and it marks the position at which we measure future erosion from. So this definitive point is either the cliff top taken from LiDAR and aerial images, or it's the back of the beach where vegetation occurs, or a defence line if one is present. The top of the cliff has always been used by NSERM and continues to be the point of definition in the new data. And we use the top of the cliff rather than the cliff toe because the top of the cliff is the point closest to the receptors at risk of that erosion impact. We use the most recent LiDAR and aerial photography from the regional network of national coastal monitoring programs, which ranged in data capture time from 2018 through to 2022. And the project used a semi-automated approach to define the cliff top by running the LiDAR through a delineation tool called Cliff Metrics, which extracts elevation profiles across the cliff face. This was used because aerial photography suffers from a phenomenon called the tumbling effect, where features with an abrupt step change in height can seem to lean in a particular direction due to variations in height and angle of image capture. LiDAR also mostly overcomes the issue of vegetation cover obscuring cliff features. The reason it was only a semi-automated approach was due to the extensive quality control carried out by the teams to verify the output line and remove any outliers. For the non-cliff locations, the back of beach position used the aerial imagery from the Coast Monitoring Programme to define the seaward edge of relatively permanent terrestrial vegetation. And as I've mentioned, where a solid defence structure was present, the NSERM feature line followed that structure. Of course, the coastline is not simple and it does not conform to an easy definitive line to pick for a top of cliff. So we devised a rule base for selecting the position of the feature line, which was based on the coastal profile and the assumption that land in front of that selected feature line would have been previously activated by erosion processes. This feature line moves all the way around the country. It's split up into approximately 7,000 frontages, each with a unique ID number. And these splits reflect changes in the variables of those locations which influence erosion potential, such as the geology, defences, exposure, and shoreline management plan policy units. These alongshore extents were defined in the original NSERM and for the most part have remained unchanged during this update process. Another thing to mention at this point is the selection of a base year for this feature line position. The data collected from the Coastal Monitoring Programme can take up to 5 years to obtain a full quality assured data set. And so we had a range of capture dates from 2018 to 2022 at the time of our extract. So the year 2020 was therefore selected as the baseline year for which the NSERM model would start erosion projections. And this also coincided with the base year used in our climate change methods that we applied, so quite fitting. So once we've established our starting position for our erosion projections, we obviously need to determine the future erosion rates. Now, to do this, we look at the past positional change of coastal features. So we've used historic mapping and coastal monitoring data, and we analysed past positional change along nearly 8,000 transects and calculated an overall change rate for each one of those transects. This was conducted for undefended frontages for around the last 50 years, which was considered a sufficient timeframe to inform estimation of long-term risks required for NSERM out to 2105, but also sufficiently contemporary to account for the most recent patterns of change. Where we have defended frontages, it's a bit more difficult, and we need to look at pre-defended timeframes and data, or we've also used changes in mean low water positions to infer coastal change in those locations. This assessment of past change is one of the really big improvements in the data available to the NCERM project, because we now have around 15 years of data from those coastal monitoring programs. And that information has enabled us to vastly increase the resolution of observations using data at those 8,000 transect locations. We did also measure accretion where coasts are accreting. That is included in the database. And sometimes with climate change into the future, that accretion turns into erosion during the longer epochs. But for the purposes of the mapping itself that we've published, we only show recession polygons. Once we had the underlying recession data, it went through extensive validation with local authorities. And during that initial verification process, we further assessed the underlying recession data to remove outliers, and also applied some averaging across similar frontages where it was appropriate to select a representative rate for each erosion frontage. Where no data was available due to the presence of defence structures, the rates were adopted from nearby undefended locations or by using mean low water lines as previously mentioned. And this process ensured that only the best quality data was taken through to the predictive modelling stage. So here on screen is an example of the resulting data. The underlying recession trend uses an annualized rate, which is projected linearly into the future, shown as the blue line here at the bottom. This was determined to be sufficient rather than attempting to use a stepped line showing episodic events, because extraction of a particular year or particular epoch and taking results from those particular points could end up being skewed based on where they sat on that episodic cycle. Also, it's key to remember, of course, that NCERM is a long-term predictive tool, and so episodic events are generally deemed to have been evened out over such timeframes. The graph here also shows the increases due to climate change. I'll explain what we did for that on the next slides. So this therefore gives us our underlying recession timeline from 2020 up to 2130, onto which we can then add in adjustments based on the influences of defences and shoreline management plan approaches. So climate change, how did we account for this? So NCERM now explicitly looks and accounts for climate change in terms of sea level rise and its impact on erosion and defence failure. It does not account for increases in rainfall or groundwater due to climate change, because that was too complex at a national scale for us to take on. As mentioned before, we use 3 climate scenarios, 1 present day climate and 2 increases using UKCP 18. For erosion, there are 2 different methods that we've applied. For cliffs, we have used the factors provided by the R&D project Shore and Coastal Erosion Sensitivity to accelerating sea level rise. And for non-cliffs, we've applied a geometric approach. So the first approach I wanted to present to you is a new method in which we used that research and development project. This is the first time it's been used, and it's a huge improvement, a step forward in terms of national erosion risk mapping. So this is applied to cliffed coasts, which are influenced by shore platforms and beaches, and it provides us with a multiplication factor which varies through time with rising sea levels to increase the erosion rates. The research uses the SCAPE model, soft cliff and platform erosion, to represent changes to the shore platform and to the cliff over time with increases in sea level. The research divided the coastal England into 60 regions based on coastal characteristics, allowing different sensitivities to be considered through numeric modelling. For each region, conservative sensitivity indicators were calculated. The CSI is a multiplying factor changing over time, as I've mentioned, that can then be applied to measured rates of erosion. The research was developed for application with the NCERM product, so the underlying recession rates were collected and then subjected to these sensitivity increase factors. And the methods were directly applicable to 60% of the coast. It wasn't applicable for non-cliffed coastlines, and we'll come on to how we dealt with those in a moment. And in some locations, the study considered that no data could be reliably extracted, principally due to records of historic sea level rise, and this occurred mostly in northern regions of the country. The study also identified areas of high sensitivity where erosion may be overestimated. For both instances of no data or high sensitivity, the NSERM project decided it was appropriate to borrow CSI values from areas that might be considered to be similar with respect to factors influencing the modelling. Key sensitivities were considered during the selection. These included coastal orientation and wave exposure alongside tidal range. And in the research report in particular, tidal range was deemed to be a very significant factor. So for the NSERM2 methods, it was considered appropriate to ascribe borrowed regions based on whether they were on the west or east coast and selected based on tidal range and geographic proximity. That research project is not applicable for the non-cliff frontages, such as beaches with dunes. So we've used a geometric approach, adapting the Bruin rule based on the principle that the upper beach profile will adjust to upward change in the tidal frame as a consequence of sea level rise. The main adaptation from previous applications of the Bruin rule is that NSERM2 used the upper coastal slope between mean high water and mean low water contours. The calculation provided us with an additional recession distance for sea level rise per year, which is then added to the underlying recession rate. So let's move on to how defences come into play with the NSERM product. As the title suggests here, it is only backshore defence structures, such as walls and revetments, that are formally considered in the NSERM calculations. We do not include cross-shore defences such as groins because they do not directly protect the back of the beach features during storms. Not directly, at least anyway. For defences, we need to assess their potential for failure before the erosion can start to become active. So there are two failure mechanisms employed within NSERM: structural performance, where we use deterioration of the structure itself and therefore its ability to withstand certain storm exceedances, and then undermining, which a process increases in risk as a beach is eroded and it lowers, thereby exposing the defence to deeper water and more wave energy. We also apply catch-up to the erosion rates once the defence fails, and I'll go over these in the next few slides. It's important to note that the defence data is a snapshot in time at the point of data capture, and that where specified in the shoreline management plans as no active intervention, we do assume no repairs or maintenance are carried out to existing structures. For locations with hold the line shoreline management plan policies, the defences are assumed to stay in their current condition and prevent erosion throughout. The deterioration of defences is strongly influenced by the condition of the structure and the potential for the exceedance of its performance standards. To assess the impact of deterioration of defences, we used the type of defence and the tow type and the condition of the structure and its standard performance design standard. And we collected this information by taking data already included in the NSERM dataset and updating it using local authority information, any EA datasets, and also Coastal Monitoring Programme Asset Register information. We also referenced back to the Coastal Protection Survey of England records for any pre-1990s defences. In some instances, we had to derive information from other sources such as Google Images, where some of that data was not available. So to apply the failure mechanisms to the defence assets, we used a variety of methods. For structural performance, published deterioration curves were used to obtain the estimated time in which structures of different types move from one condition grade down to the next, eventually leading to failure. A translation from this reduction in condition grade to the structural performance standard was applied so that we could look at the probability of failure. Climate change influences the loading levels on the structures by applying sea level rise. This leads to increasing water depths and wave heights and a lowering of the defence's annual exceedance probability. Undermining is a key failure mechanism, so NSERM uses an extrapolation of the reduction in beach level to determine the time until different tide levels are projected to reach that defence, therefore causing scour-induced undermining. Applying sea level rise due to climate change serves to speed up the rates of recession of a geometric application of beach lowering, which then leads to defence becoming exposed sooner in the failure timeline. The calculation of both of these processes to formulate an annual probability of exceedance curves was completed, and the model takes a higher probability from both failure mechanisms to construct a final failure curve. We've mentioned catch-up a few times. Here's a bit more information on what we did in terms of erosion catch-up. Once a defence fails, there's a period of rapid erosion that can take place. This accelerated period of erosion is determined by the length of time that a defence has been preventing that erosion. And this faster erosion takes place for a set time period before returning back to the original underlying recession rate. Despite this catch-up phenomenon being recognised since the 80s, there's been limited research into this, in part due to the relatively low number of defence failures in recent years, providing a basis for monitoring and analysis. Which has therefore been to derive estimates based on information that has come from recent studies to provide an estimate of catch-up duration. The studies suggested an average catch-up rate of between 3 and 5 times faster than historical rates. So the rate of 4 times the underlying erosion rate was taken forward. To define how long the catch-up period may take, we looked at how long the coast had been defended for, and so how much time erosion had been prevented. And we took both factors into account, and we applied the first 2/3 of erosion recession into the first 1/3 of the time frame, and then allowed a slower rate to account for the next 2/3 of the catch-up period. So we've just gone through how we determine timelines for underlying recession and also defence failure. The next step in the process was to combine these to provide our final erosion recession distance over time. Of course, there is the added complexity of the management intents from the shoreline management plans, and we'll pick up on that in a moment. For a simple example, though, let's take a frontage which is presently defended, and we're going to use our no future intervention modelling scenario where no maintenance or replacement is carried out for that defence. So as you can see, there is a period of no recession at the start of the timeline where the defence is in place and it's performing its role. Failure then happens and erosion catch-up process kicks in with accelerated erosion until the shoreline re-establishes a more natural behaviour where the underlying recession rate then applies. And you can see how climate change influences this in the graph on screen by bringing that failure of defences earlier in the time frame and increasing the erosion risk shown by the dotted lines. So how do the shoreline management plans influence NSERM? So a big impetus for the revision of the NSERM methods was due to the Shoreline Management Plan Refresh project, where the SMPs could now provide additional detail and granularity about the proposed future management intents along our coastline. This provided subcategories against the headline management intentions of hold the line, no active intervention and managed realignment. And NSERM needs to make an assumption that future management follows what is set out in these long-term plans. So the modelling process cannot consider the unknowns of funding or shifts in management intent. It just takes it as written in the shoreline management plans. With the SMP first epoch only going out to 2025, that therefore being reached by our publication date of the new NSERM information, the model started with a simple defended or undefended status, depending on what's currently in place on the ground. We then interpreted and rationalised the information within the shoreline management plans to assign one of 3 states to each frontage for the remaining 2 epochs up to 2055 and up to the year 2105. And these were either erosion restricted, erosion unrestricted, or stopped maintaining. So we saw previously how the no future intervention timelines look. Here is how the timelines for the with SMP delivered scenarios look based on the 3 states I've just mentioned. Firstly, where erosion is restricted, obviously no recession occurs throughout the timeline. Remember that we don't account for any residual risk behind those defences. When erosion is unrestricted under a no active intervention intent, erosion continues at the underlying recession rate and it's influenced by climate change. In the third image, we shift from a defended situation to a no active intervention scenario, and progressive failure of defences occurs, producing that step recession timeline that we've previously seen. We have assumed defaults of the transitions at the SMP epoch breakpoints, but of course, in reality, those years of change between one management scenario and another are much less rigid. Where a policy was for managed realignment, a decision was made based on the SMP detail to set the data transition from erosion restricted to unrestricted, or vice versa, to reflect that intended management approach. Confidence ratings. So one of the big changes in this iteration of NSERM is the removal of the confidence band approach. Previously, we provided 95, 50 and 5% confidence bands, but we have shifted to representing a range of results based on climate change scenarios instead. And we represent the best estimate erosion prediction. We have developed a new confidence rating approach, which is applied to each individual frontage, and that represents the confidence in the source of the data and the methods that we use. So we start by applying confidence sub-ratings to the recession and defence data source, climate change, defence and catch-up methods. And the table on the screen here shows the weightings applied to the erosion and recession source data. And you can see that those increase with increasing confidence in the data source, with local studies and direct measurements being highest rated. In this way, we can identify which aspects of the data and calculations processes are bringing in uncertainty, and we can identify options for future improvements to increase our confidence in the end result. So these sub-ratings are then combined to provide an overall confidence rating for each erosion projection on a scale of 0 to 1. These are then split into categories and assigned confidence labels ranging from low to high. This is an example of one of the distributions from a long-term 2105 scenario. So how do we use all of those methods to actually produce the risk zones on a map? In essence, it's relatively simple. We create a polygon buffer of potential erosion distance from the NSERM feature line moving inland. We produce polygons for each of the climate and management scenarios for the years 2055 and 2105. As shown on the right-hand picture, we include the area between mean high water springs and the NSERM feature line position in all of our risk polygons. And that's to show that this area is also at risk of the impacts of erosion, as there's often infrastructure in those locations. The risk buffers are then merged in GIS processes to create smoothing, but they are also post-processed so that they then retain their individual attributes. And this allows users to click on a polygon, see the underlying data. The polygons retain their own recession distance attribute, as well as displaying any adjacent buffer distance that overlaps them, so that users can understand how they've been created. Lateral buffers do not extend across things like hold the line frontages because they are protected from erosion, so we don't buffer over those. And buffers do not extend over the floodable frontages because this led to erosion zones spanning over areas of open water. So there will be instances that you can see on the image on the right hand side here where you'll see a straight edged termination to the polygon. Whilst that seems artificial, it's no more or less artificial than creating an arbitrary extension with a buffer. And it's important to remember, of course, that the NSERM data set does not map the future coastline position. Its purpose is there to highlight potential areas of risk. Areas of complex geology. where deep-seated landslides can occur were previously known as complex cliffs in NSERM, but they were not displayed spatially, and that was always a bit of a limitation. So we've worked on improving the assessment and how to present these visually. Following consultation with local authorities through alpha and beta testing, we renamed the complex cliff locations as ground instability zones that better reflects the risk, and it's more meaningful than the term complex cliffs. So we re-evaluated these features, recording rear scarp, bench, sea cliff positions, and worked with local authorities to assess movement potentials. We have the standard NSERM erosion scenarios presented at the cliff base, but we now also display a potential ground instability zone between the sea cliff and the rear scarp to show the area which has been previously activated, either historically or recently. And we also show a potential zone of future ground instability. And that potential future zone is based on future coast data for recession and frequency potential within the next 100 years. Because complex landslides are so unpredictable and their episodes can span years or centuries, we have not tied these zones to the SMP epochs, which is why we've used a single risk envelope for that 100-year period. We've also not included climate change on the ground instability zones due to how complex the interaction of increased rainfall and groundwater are, and the lack of any method to apply that at a national scale. We've also sought advice from local authorities through this process and included additional wording on the Shoreline Management Plan Explorer website, which points people to the direction of local authorities for more information. And we have site-specific text from those key sites on our Explorer platform. We've got 3 more slides left, so we will make sure that we have some time for discussion in a moment. So we've used the new NSERM polygons to count numbers of properties at risk. The analysis uses the new National Receptors dataset for 2023. It also uses the Ordnance Survey Master Map building footprints so that any partial overlap of buildings is accounted for. We've counted residential and non-residential properties, and we followed our Environment Agency guidance for which property types to include. The numbers nationally have differed from our previous assessments. That's due to the differences and improvements that we've applied not only to the NSERM methods and polygons themselves, but also by including climate change in those, and also by using the new National Receptors dataset as well. We have extended the assessment to include critical infrastructure such as road and rail. We've included landfill, agriculture, SSSI scheduled monuments, and also looked at property damage assessments as well. So how do you access all of this new information? We host the NSERM data on the SMP Explorer platform where it's available. It's also available to you as open data from data.gov.uk and via web map service links. So you'll be able to access all of the scenarios that we've discussed today on those platforms. A professional user version is available, which contains some more detailed attribute information as well upon request and conditional licensing from ourselves. That concludes my presentation. There's a lot of information there, but I hope that you have found it useful and also found it interesting. I look forward to hearing your thoughts and comments and any questions. I'll pass back over to you, Nish. Thanks.
That's great. Oh, thank you so much, Ben, for such an interesting talk. It's really interesting to see how geomorphology can be, really informative at a sort of national strategic scale for this sort of mapping project. Well, yeah, so now I think, waste no time and hand over to the floor. You should be able to hopefully unmute yourselves and turn cameras on. I can also see there's a couple of questions in the chat, so maybe I'll just start with those whilst people have a little think and they can put their hands up whilst we're addressing these ones in the chat. The first one is somebody's asked, they're wondering about why it takes as long as 5 years to assure the data. Is that a bit too long, perhaps?
Yeah, I can take that one. Thank you. It's a good question. Basically, the Coastal Monitoring Programme assesses the whole coastline of England, and that's split down into regions. flying LiDAR flights. They're programmed within a 5-year program, essentially, within that work. So whilst it only takes a year or so to fly one section, being able to have the whole of the country completed by a certain time can take that long in between data sets. So the most recent LiDAR flight, let's say for somewhere in northeastern England, maybe 2018, whereas the most recent data set available to us for, let's say, the southwest of England, may be much more recent, around 2022. So we had to balance that, and we can only work with the data capture that is available to us. And of course, the QA for those does take some time, but it's not, to be clear, it doesn't take 5 years for you to fly LiDAR in one location and quality assure it and publish it. It's just the amalgamation of the whole country's worth of data that can take that long.
That's great, thank you. And there's another one here from Alistair Rennie asking about the method to calculate, catch-up erosion based on the duration of the historic protection it's given. So you must have needed to know, how long this is, how long this is for each defence, how long each defence has been in place, giving that length of protection. How did you get the information to inform this? How reliable is it? Did you get it from historic mapping or other ways?
Yeah, a great question. Thank you very much. Essentially you've put some of the answers in the question for me. We used historic mapping to see where we could identify where a defence or where a coastline had been defended. Obviously those are only periodically published, so there is a span of data, or time rather, where it may have been a defence may have been installed and not published onto a map for a certain number of years. Historic data on defences, in terms of engineering records and things, it's great if you have them, but moving that far back in time, often that isn't the case. So we do have to make some assumptions, and we do have to go with the best information that we can find. And yeah, you're absolutely right. In some locations, you could be a few years out.
That's great. Now, has anyone got any other questions they'd like to ask Ben? Feel free to put your hands up if you do. Otherwise, I will get to ask one. But no, Nick's gone for it. Go for it, Nick.
Hi there. Thanks for the talk, Ben. It's really good. My question is really narrow, so I didn't pipe up straight away. But it's just talking about the identification of receptors. What I've found up here in Scotland is that you may be identifying sites of special scientific interest as a receptor, purely on a factual basis. There is an overlap. What I found, local authorities tend to interpret that as risk to that site. And that's a sort of risk to nature conservation because it's a misuse of the results. The nature of the features of SSSIs can vary so much through geological, coastal geomorphology, habitats, etc., that whether or not coastal recession is a risk can massively vary. So it's something you do need extreme care with, I think.
Yeah, absolutely. Yeah, indeed. In some places that could actually be a wanted result to allow those processes to happen rather than a risk, as you point out. Yeah. We looked at that in terms of picking up triple SIs purely as a bit of an exploratory basis, to be honest, just to look at what kind of coverage in total that we had as triple SIs included. Same things for things like scheduled monuments and agriculture. So these are quite useful and quite helpful to give us a national picture at a very high level of the scale of potential impact all the way into those future time periods. But absolutely, if you're going to be using it at a more local level for particular things and particular investigations, you definitely have to take account of those things you pointed out. Indeed.
And I can't help myself but jump on that as well with regards to triple SIs. I guess of potential more interest for with regards to protected sites is where sites are designated for cliff interest features, where those where the cliff lines are, to look at where cliff lines might actually roll outside of the SSI boundary, I think would be of particular use to look at, rather than where the cliff line is going to impact the size of the SSI, perhaps the other angle of where it's going to leave and therefore not be technically legally protected anymore. Because yes, it's not a mobile boundary, unfortunately.
Yeah, and I think that's one of the key things to bear in mind. This is, you can use NSERM in quite a strategic manner, looking out to those longer epochs, to try to think where some of the plans and management practices that you may wish to use in the future may need adjusting, may need changing. And hopefully, with it being such a long-term data set, it provides people with the lead time to start those decisions.
Great. We certainly have lots of plans at Natural England to use the data. It will be really useful for us at a strategic scale. Has anyone else got any questions? If so, put up your hands or put them in the chat. Oh, here we go. We've got one in the chat here. So they're asking, how are we looking to look at how we're going to compensate the loss of biodiversity / SSI due to coastal erosion in the short term and the long term, as erosion is not going to just stop. It's going to sort of affect, slowly impact those sites.
I think that's why we've got people like yourselves on calls like this, isn't it? So that we can start to try to answer those questions. How do we use the information that we've got to tackle these things in the most appropriate way for not only our communities along the coast, but also our biodiversity and our environment as well. So we need to bring in thoughts around adaptive management. How can we better look at managing our coastlines in the future that is not only sensitive to those things, but doesn't necessarily follow our defence methods that we currently have used. So yeah, I think looking at how we may compensate in terms of biodiversity and SSIs really is a case of identifying what we value in those adaptation measures into the future and working out the right balance for them.
Absolutely. Thanks for that. Any more questions? We've only got 5 minutes left, so not a huge amount of time, but if anyone's got anything to ask, I'll jump in the meantime. I'm just interested in the relationship that there is between eroding sites and flooding sites, and the fact that it's, although we've obviously split sites into erodible and floodable for the purposes of these mapping projects, NAFRA and NSERM, is there any potential in future to sort of combine mapping and try to work out where those interactions lie?
Yes, there is. It's incredibly complicated, which is why the original NSERM developed back in 2005 to 2010, which is why we put splits in for floodable and erodible coastlines, predominantly with NSERM just picking up the higher ground, which wasn't at flood risk, but there were locations identified where the erosion processes were important, even on a floodable frontage, and so those were included. So it's not as cut and dry really as it may seem at first glance. Moving into the future, one of the recommendations that we have had through the project is to look at a wider adoption of NSERM predictions along the coast, so that we can really start to look at those joint processes for coastal change, looking at flood risk and erosion risk together, because often they are not isolated impacts as well. So yes, in the future we will be. It's a complicated picture already. I'm sure it will continue to be so, but we do plan to try to expand that in the future.
Great to hear. I think there's just one little question left in the chat, asking about whether the LiDAR data used will be available for open access. I'm assuming it already is, but yeah.
So it's not available for open access via through the NSERM work. But if you take a look at the Channel Coastal Observatory website, and then you should be able to see what you can and can't access for your particular research or other interests. So quick answer is I don't know if it's all open data for all uses. I've got a feeling it might not be, but that Channel Coastal Observatory, and Ollie's just put a link in there for you into the chat. Go and check that out, and hopefully you'll be able to get what you need.
And it's in the metadata as well, isn't it? That like what LiDAR was used, presumably.
Yeah.
So that so hopefully that should be something to follow up for anyone who's interested. That's great. Well, I think we'll probably draw it to a close there, as we're pretty much at 2 o'clock. But thanks, Ben, so much for presenting to us today. It's been really great to have you on board, and like I said, the presentation will be up on the YouTube channel at a later date, so anyone who missed it can go and have a look. If you think that anyone might be interested, please do tell them it will be available up there. But that's great, thank you, and I'll let you all get on with your days. Thank you very much. Bye.
Thanks all. Bye.